Hello, everyone, and thank you for attending the Steel Joist Institute's webinar, Economic Floor Systems with Composite Steel Joists. My name is Patty, and I will be moderating today's webinar. Today's presenters are Dave Samuelson with Volcraft and Sam Ferris with New Millennium.
All right, thank you, Patty. Hello, everyone, and thank you for logging in. My name is Sam Ferris. I'm a structural engineer with New Millennium Building System. The composite steel construction has been well known for a number of years as an attractive option and as one of the most economical systems for constructing building floors in commercial and residential buildings. It is an economical system because we are optimizing the material usage. Concrete is stronger in compression and steel is stronger in tension. By using the action of these two, the advantages of both materials are utilized to the fullest. Composite and non-composite steel joists are utilized to support concrete floor systems, but this webinar will focus on information contained within SGI's two future publications. The first one is the standard specifications for composite steel joists, second edition, and the second publication is Technical Digest number 13. CJ-Series joists utilize shear studs welded through the steel deck to the underlying top chord angles of the steel joist. The steel joist top chord typically are fabricated utilizing hot rolled or cold formed steel angles. A typical 1-inch horizontal gap between the top chord angles, and because of this gap, this requires that the shear studs be welded to the top chord horizontal legs on either side of this gap. In this picture, you see shear studs staggered within one deck rib. The stud's shear strength is dependent on the position of the studs and how many studs within a deck rib. By the position of the studs, I mean whether the stud is in the strong position or weak position, and we'll talk about that in more in detail. I will also discuss in detail guidelines for the installation of the shear stud onto the top chord of the CJ-Series joist. This is a picture during construction of a 144,000 square feet facility that provides a home office space for Owens and Minor Incorporation in Virginia. As you can see in this picture, shear studs welded through composite steel deck to the underlying top chord angles of the CJ-Series joist. Composite steel joists used on this project have a depth of 44 inches, spaced at 9 feet, and span 60 feet. This provides a very efficient floor system. The concrete slab total depth is 6 inches and is supported by 3 inches composite steel deck. In the future, SGI is releasing the second edition CJ catalog. On the cover of the catalog is a picture of a recreational center at the University of Colorado. What's interesting about this project, CJ-Series joists support open air tennis courts on the top of the floor. Some information about this project regarding joists: the joist span 116 feet. Joist depth is 76 inches. Joists are spaced 7 foot on center. Concrete slab total depth of 5 1/4 inch, supported by 2 inches composite steel deck. Lightweight concrete was used. F prime C was or is 3.5 KSI. Now we'll talk about what are the different elements that make up the composite joist system. The system utilizes open web steel joists. The steel joists are simply supported and are generally not considered part of the lateral load resisting system. The concrete slab is connected to the joist top chord with shear studs, and the concrete slab acts as the compression cord element during the composite stage, but during the pre-composite stage, the joist or the steel joist top chord is the compression cord element. Composite action relies on shear connectors, that is, shear studs, to transfer the horizontal shear between the slab and the steel joist. This will eliminate the slip between the steel joist and the concrete slab and allow them to act together structurally as a single unit. Meaning this will ensure a single linear strain from top of the concrete slab to the bottom of the steel section. Now, what are the key advantages or benefits of using SGI's CJ-Series Composite Joists? Composite steel joists provide a number of advantages. First one, mechanical ducts, plumbing pipes, electrical conduits can readily pass through a CJ-Series open web system in lieu of running them beneath the joist bottom chord. This permits reduction in floor-to-floor height. By minimizing the floor-to-floor height, you reduce construction costs and add additional square footage without exceeding height limitations. Another advantage, when there is a large mechanical duct and the standard width triangular opening is not large enough to fit it through, the joist manufacturer provides and designs customized panel configuration and width openings. We refer to this opening as rectangular verandil opening as shown. Rectangular verandil openings are ideally located near the midspan of the steel joist for typical uniformly loaded joists. And the reason for that, the vertical shear near the midspan of the joist is at a minimum value at this location, resulting in the lightest CJ-Series joist possible. But there is a limitation. The maximum width of the verandil opening is commonly no greater than 2 times the depth of the CJ-Series steel joist. Nowadays, with everybody's using building information modeling, BIM, widely used, and this allows the location and size of ducts, pipes to be accurately coordinated, and BIM will detect any clash before the CJ-Series joists are even erected. Another advantage is the maximum span to depth ratio of 30, and this permits the use of shallower joists for any given span. For non-composite joists, span to depth ratio is 24. Efficient composite design makes it possible to span greater distances. These larger spans result in larger column spacing, allowing increased flexibility for laying out floor plans. By having larger open areas, this increases the potential rental value of the floor. Another advantage for composite steel joists, they are more efficient and economical because both steel and concrete are utilized effectively. This efficient system allows a reduction in the joist weight for any given joist depth. Lighter weight joists translate into lighter weight columns, reduce foundation costs. And reduction in building weight also ultimately results in savings to the building owner. Another primary advantage is with respect to deflection. Concrete floor systems and the supporting steel joists are integrally connected with shear studs This composite action provides a stiffer floor system that deflects as a single unit, reducing live load deflection significantly. Efficient erection, also another advantage of the CJ-Series joist system, minimizes construction time and permits early occupancy of the building. Wider joist spacing reduces the number of steel joists to be erected and fireproof. Now, how do you designate a CJ-Series composite steel joist like on the floor plan? CJ-Series composite steel joists are designated following the standard format. You start out with the joist depth, then two letters CJ for composite joist, followed by the total factored composite design load, then total factored composite live load, and finally total factored composite dead load. So in this example, the joist depth is 30 inch. This must be provided in inches. This depth includes the steel joist portion only, not the deck slab. The 2188 PLF is the total factored composite design load. The 1168 PLF is the total factored composite live load. And finally, the 420 PLF is the total factored composite dead load. Now we'll talk about the seats. CJ-Series are typically provided with a standard joist seat unless special bearing conditions are required. We'll talk about that some more. As shown in the right detail, two bearing seats angles are typically welded to the joist top chord to create a combined I-shaped section. CJ-Series joist seats can be either welded or bolted to their structural support. Steel Joist Institute recommends a minimum seat depth of 5 inches, and I will explain why in a few slides. But sometimes, for CJ-Series joist, the joist manufacturer has to fabricate special bearings like flush framed bolted connections. In the left photo, a 1-inch thick plate, commonly referred to as knife plate, has been placed between the top and bottom chord angles. This knife plate simply bolts into a steel shear plate attached to the wide flange girder. The advantage of this connection being that the steel deck can be placed flush across the CJ-Series joist and steel girder. This facilitates the installation of welded shear studs to the top flange of the wide flange girder, which in turn permits the wide flange girder to be designed compositely. On the other hand, in the detail shown to the right, again, a 1-inch thick knife plate has been placed between the top and bottom chords. In this instance, the knife plate is bolted to a pair of double angles welded to the concrete wall steel embedment plate. Earlier, I said SGI recommends a minimum seat depth of 5 inches. So when the joist seat is 5 inches or more, the central axis of the end tension web ideally passes near the intersection of the central axis of the joist top chord and the joist end reaction. So you have no eccentricity. However, when the joist seat is 2.5 inches and the end tension web is double angle as shown in the detail, an eccentricity is present because the central axis of the end tension web, joist top chord, and end reaction don't intersect at one point, which results in some eccentricity. So the joist manufacturer has to design the joist top chord for this moment due to eccentricity, in addition to the end panel chord moment from applied loads between the reaction and interior top chord panel point. Now we'll talk about what are the design requirements for CJ-Series joist components. Design requirements were developed based on extensive full-scale experimental testing that had been completed on CJ-Series composite joists in the past 30 years. Researchers carefully studied the behavior of the bottom chord, top chord, webs, and shear studs on a wide range of CJ-Series joists. Now we'll talk about the experimental test instrumentation. As I said earlier, extensive researches were performed on composite steel joists at the University of Minnesota, University of Nebraska, and Virginia Tech. Every full-scale test specimen was extensively instrumented with strain gauges located at the mid-span, quarter point, and end of each joist. The slip of concrete slab relative to steel joist top chord was carefully measured utilizing slip gauges. Deflection of the composite joist at the mid-span and quarter point were recorded. Now, I will present to you the research findings on how each component of the composite steel joist behaved during the test. We'll start off with the bottom chord behavior. As a composite joist is loaded, the bottom chord elastically strains as shown with the straight red line. In this stage, if the load is removed from the joist, no permanent deflection or deformation within the joist will be noted, and the joist will return to its original vertical position. When we're designing a composite joist, the ASB service load typically stresses the bottom chord to no more than 0.6 times the yield strength of the bottom chord. As you can see from the plot, at this low stress level, the CJ-Series joist is perfectly elastic. Now, if you continue to load the CJ-Series joist, you will eventually start to yield the bottom chord, as shown with the upper line. The bottom chord continues to yield as additional load is applied. As shown in the plot, there is a slight curvature in the aqua line, indicating some strain hardening occurring in the bottom chord, which permits the bottom chord to carry a small amount of additional load over and above the first yield load. Eventually, the CJ-Series reaches ultimate load. This is a picture of a composite joist tested at Virginia Tech. If you look at this photo, the bottom chord is extensively yielding in the middle quarter span of the joist. And what I find interesting, the center line deflection is approaching 12 inches, which is like span over 50. And look at the concrete slab, it's still intact with this much of deflection. When we're designing composite joists, we don't want, want a brittle concrete crushing to be the controlling limit state. Instead, if a composite joist floor system should ever be grossly overloaded, you want a floor system that provides plenty of visual warning, providing you ample opportunity to remove excess live load. This composite joist system performs in a ductile manner, which is highly desirable. Now we'll look into the top chord behavior during the test. During the pre-composite stage, when the weight of the concrete is placed on a composite joist, the joist at this point in time acts non-compositely. In other words, the shear connectors are unable to transfer any load through the wet concrete into the concrete slab. This can be seen in the plot, the initial red line, which shows the strain taking place in the joist top chord as the concrete is being placed on CJ-Series span. So now the steel joist top chord is the compression element. Negative strains in the plot represents the compression strain in the joist top chord. Now, once the concrete has hardened, any additional load is transferred directly into the concrete slab as shown. Note that there is no applicable increase in the top chord strain as load is being applied to the composite joist. So now the concrete slab is the compression element. Once the bottom chord starts to yield, if sufficient shear connection is provided, the top chord can actually go into tension. This can be seen with the aqua line turning to the right, where the prior compressive strain in the top chord is reduced and the top chord develops a slight tension force in it. Now, once the shear connection starts to slowly fail, that means we're looking at partial composite action. The compression in the top chord starts to build back up, because now the steel joist top chord is carrying the load. Now, we look at the web behavior. Webs in a compression joist behave identically to webs found in a non-composite joist. This is a plot for a joist web member in tension. The web in a composite joist must transfer the increasing vertical shear load to the end of the joist. You can see in the plot the linear increase in tensile force within a tension web member. Once the bottom chord starts to yield, the tensile force or the tensile force in the web gradually decreases as seen by the aqua line. Now we'll look at what forces each element of the composite joist is designed for. Top chord is designed for compressive force from non-composite dead load plus construction live load, followed by a total composite load case check, and I will talk about that later on. Bottom chord is designed for tension forces from composite dead and live loads. Webs is designed to carry total vertical shear. Shear connectors or shear studs apply to fully develop the bottom chord yield strength. Concrete slab is analyzed using the transform area concept. Deflection under composite load is analyzed using composite moment of inertia. Now, how do we calculate or determine the composite design moment capacity for composite joists? The moment capacity of a composite joist can be calculated using the simple model. The ultimate strength model for a composite joist is no different than the ultimate strength model for a composite wide flange beam. At ultimate strength, the tension force in the bottom chord is simply the area of the bottom chord times the yield strength of the bottom chord. And for yield strength, we assume 50 KSI. The tensile force is assumed to act at the centroid of the bottom chord. On the opposite side, the compression in the concrete is simply 0.85 times F prime C times A, and A is the assumed depth of concrete compressive block. times the concrete effective width, B sub E, and the compressive force is assumed to act as the centroid of the compressive block. Note in this model, during composite stage, we are ignoring any forces in the joist top chord. That is true if sufficient shear connection has been installed to fully yield the joist bottom chord. If less shear connection, like a partial shear connection or partial composite action had been, so if you have less shear studs, there will be a compressive force in the top chord. So part of the load is being supported by the steel joist alone. The effective distance, D sub E, between the centroid of the tension bottom chord and the centroid of the concrete compression block is calculated using a concrete stress of 0.85 F prime C and an effective concrete width as shown. The concrete effective width is calculated identical to that assumed for a composite wide flange beam. Now, as we all know, the philosophy of design, or the expression for the structural safety requirement, is as shown. The required flexure strength determined from applied load, factored load, which is M sub U, and phi M sub N, which is it has to be less or equal the minimum design flexure strength of composite section. This minimum design flexure strength of composite section depends on the controlling limit state. There are 4 limit states to be investigated, and the controlling limit state is the lowest value of the 4 limit states. The first limit state is the bottom chord tensile yielding, where A sub B is the cross-sectional area of steel joist bottom chord. The second limit state is the bottom chord tensile rupture. The third limit state is concrete crushing. And the fourth limit state is the shear connector strength, where N is the number of shear studs between the point of maximum moment and zero moment. Q sub N is the shear capacity of a single shear stud, and we'll talk about it in more detail. And A sub B is the cross-sectional area of steel joist bottom chord. We do also additional checks. The steel joist alone must be designed for the pre-composite stage. The top chord must carry the full pre-composite load, non-compositely. Webs and bottom chord angles are designed for the total factored composite design load. Differential shear at the top chord panel points is checked also. The top chord end panel must carry the full composite load until the shear studs transfer load up into the slab, because you're going to have enough studs to develop the full composite action near the end of the joist. The top chord must have sufficient thickness for attachment of studs, and I will talk about that in the next slide. Usually the CJ series top chords are approximately 50–70% of the area of the bottom chord. Now, as you can see in this table defines suggested minimum horizontal top chord leg length and leg thicknesses. And why do we need a minimum horizontal leg for installing studs? Because leg lengths less than those shown in the table makes installation of welded shear studs difficult. And also, in the table, minimum top chord thickness is required. So for each stud diameter, like if you look at 3/4 inch stud diameter, a minimum leg thickness of a quarter. And this is to keep the stud diameter to top core thickness ratio less or equal 3. 3 is the highest SGI permitted value for this ratio. AISC allows a different limit, and we'll talk about that. Now, we'll talk about the painting of CJ-Series joists. The standard shop practice is to furnish composite joists unpainted because paint hinders installation of welded shear studs. By that I mean shear connector weld quality might be compromised. In rare instances, CJ-Series joists have been provided with joists top core unpainted, as you see in the picture. Now, how do we install at the job site? How do we install shear studs? You mark the location of top core with a chalk line, and note the 2 blue chalk lines in the right photo, indicating where the center of each joist top core leg is located. Deck must be tight against top core. Remember earlier I said the stud diameter to top core thickness ratio is 3 for SGI, that's what SGI limit is. But for AISC, it requires to be less or equal to 2.5. But with the SGI testing, we apply a reduction in the stud capacity. It is preferred to place shear studs in the strong position, but SGI has conservatively assumed studs will be installed in the weak position, and I will explain the difference between strong and weak position. The 3/4 inch diameter shear studs were being installed at a rate of 220 studs per hour to the CJ-Series joist. This stud installation rate is very equivalent to the stud installation rate for wide flange beams. Another thing to watch for, studs shall be alternately placed on each chord angle section for double angles top chord. The intent of this provision is to strive to distribute the shear load from the shear connectors into both joist top chord angles, as versus installing all shear studs on only one top chord angle. But when this is not doable or possible, we have to apply other limits. The first limit is no more than 3 studs shall be placed consecutively on any one chord angle, and no more than 60% of the total number of studs shall be placed on any one chord angle. Now we'll talk about the shear stud strength and what are the factors that affect the shear stud strength. When a composite joist is loaded, the concrete slab wants to slip relative to the joist top chord toward each end of the joist. The shear studs are there. They are connected to the joist top chord to ensure no relative slip occurs between the concrete slab and the joist top chord. The shear capacity of the connector alone does not determine the composite shear strength, because cracking of the concrete in the deck flutes could reduce the shear transfer capacity. As you can see in the picture on the right here, shear studs located near the left joist support following a full-scale load test. Note how the shear stud is bent to the left by the concrete slab moving from right to left. Now, what do we mean by shear studs in strong position? The details show what is referred to as a shear stud installed in the strong position. The strongest position for a welded shear stud occurs when the shear stud is located as far as possible from the mid-span of the joist as shown in the bottom detail. The steel composite deck has a stiffening rib located at the center of the bottom deck rib. This requires the welded shear stud be placed on either side of this stiffening rib. Looking at the upper right cross-section, you will note that there is a considerable concrete between the shear stud and edge of the deck rib to the right. As the concrete wants to slip from right to left, this thick concrete is not readily crushed by the shank of the shear stud. This is the reason why shear studs placed in strong position has increased shear capacity. On the other hand, when the shear studs are placed on the side of the deck, stiffening rib toward the mid-span of the joist, there is reduced concrete cover between the edge of the shear stud and the edge of the deck rib to the right. As the concrete bears on the right side of the shear stud, the concrete on the edge of the stud can be crushed, permitting the stud to plow through the edge of the deck rib, as shown in the upper right photo. You see the picture on the right. As a result, the stud is in weak position and it develops a reduced shear stud capacity. Now we'll talk about the transverse shear stud spacing. The shear stud transverse spacings shown in these details are no different than those suggested by the AISC Steel Construction Manual. The studs shall be transversely spaced a minimum of 4 times the stud diameter when shear stud pairs are placed side by side within one deck rib. However, when shear studs are staggered within one deck rib, a minimum transverse spacing is 3 times the stud diameter. Now, as far as the longitudinal shear stud spacing, the shear stud longitudinal spacings are no different than those suggested by AISC Steel Construction Manual. It is 6 times the stud diameter, except when studs are placed within the same deck rib. But when studs are placed within the same deck rib, a minimum longitudinal spacing is 4 times the stud diameter. There is also a maximum limit. This maximum spacing shall not exceed 36 inches or 8 times the total concrete slab depth. There is also a minimum edge or end distance for shear studs. The minimum longitudinal edge distance for end shear studs, so that X needs to be greater or equal deck height plus 4 times the stud diameter. The minimum transverse edge distance for shear studs needs to be greater or equal 6 inches. Now, I told you before about Q sub n, which is the shear stud capacity. The shear stud, or the shear capacity of a single shear stud, Q sub n, depends on the stud diameter top chord thickness ratio. And you can see it's also dependent on the group effect factor, R sub G, which is equal to 1 for 1 stud per rib, and it's equal to 0.85 for 2 studs per rib, side by side, and it's equal to 0.7 for 3 studs per rib, side by side. And also R sub P, which is the position effect factor, and I will explain the values in the next slide. R sub P values are based on assuming that the shear studs have been installed in the weak deck position. And as you can see, it's, based on the deck height, the average deck rib width of the deck, and also the stud diameter, you obtain your value.
My name is David Samuelson. I'm a structural engineer with Nucor's Group Technical Services. I've had the opportunity to be involved with testing and researching of composite steel joists for the last 30 years. In the last 18 years, I've chaired the SGI's Composite Joist subcommittee. So this is a topic that's very dear to my heart, and I welcome everyone for joining our webinar today. So the actual International Building Code 2015 makes reference to the SGI CJ-Series joists, and of course the standard deflections for a CJ-Series joist, typical limit on live load deflection typically is L over 360, and typical combined dead and live load deflection at L over 240. So that's very typical of any floor system. One of the questions that I get many times is the question about long-term deflections of a composite joist. And that's something that we've looked at. It's generally not anything that a person needs to worry about. The long-term deflections are very small. And what I'm talking about is the deflections that would result as the concrete has small amounts of shrinkage within the concrete itself. The actual amount of deflection, long-term deflection, is dependent on the water cement ratio of the concrete aggregates, the amount of small amounts of crete. Generally, those shrinkages are very, very small, and it's really nothing that has any really effect on the behavior of the joist itself. One of the typical questions that I get a lot is with regard to cambering of composite steel joists, and it's typical practice for a SGI member company to provide camber in the composite joist. And the reason we do that is that we want to make sure that the floor comes out flat, preferably when the concrete has been placed on the composite joist itself. And there's really two options that you as a specifier can consider. Option one is the most common option that most engineers elect, and that is that they camber for 100% of the non-composite dead load, that being the dead load from that of the steel joist, the steel deck, and the concrete slab. So when you actually place the concrete on the joist, the initial camber will come out and will result in a flat slab. The other option is you can potentially camber slightly additional camber if you want to have a slightly positive camber after the wet concrete has been placed. If you were to do that, you would not want to camber for the full amount of composite dead load and composite live load. You'd want to use a reduced amount of those loads to more accurately reflect what the actual loading on the floor is. So this is just a schematic showing greatly exaggerated the camber in a composite steel joist. And so the recommended way for placing concrete on a cambered steel joist is to provide the concrete at a constant thickness over the top of the joist. And the reason being is that if you attempt to come in and say shoot levels on this type of floor, what you're going to be doing is you may have the floor level, but as you add concrete to the balance of the remaining portion of the span, that concrete is going to go, the joist is going to deflect down, and you're going to end up chasing your tail. I've seen many jobs where they've attempted to use transits, and you end up with a non-uniform thickness of the concrete. You're much better off placing the concrete to a uniform thickness. And there's really a couple ways of doing that as far as placing the concrete to a uniform thickness. In talking with a very large contractor, what he shared with me is it's very common for them to use a probe. Now let's just say that this particular concrete slab here that were designed with a total thickness of 6 inches. So they've got a probe that's marked at 6 inches. What they do, they strike off the concrete at that 6-inch depth along the span and create what I will call a wet screed. And you proceed down the span, and you also strike off the concrete so that you're able then to get a uniform thickness of concrete on the joist itself. If you end up with too thin of concrete, you can end up with potentially the shear studs coming near the surface, and also you would have a reduced potential of fire protection. So it really works well if you just place the concrete to a uniform thickness. We've done hundreds and hundreds of jobs, and the floors come out perfectly flat. One of the common things that engineers add is typically there'll be a layer of welded wire fabric that's placed in the concrete, and or certain types of fiber mesh. It's very common for engineers, particularly over the girders, to place sections of rebar over the girders, and what that does is that will reduce any type of superficial surface cracking of the slab. The composite joists are assumed to be simply supported with the typical end connections, so there is a tendency to generate some small negative moments in the surface of the concrete over the girders. So placing these short sections of rebar holds those surface cracks, if any, that would appear together. So it's just a more of a serviceability recommendation. As far as actual placing of the concrete, of course, that can be done by either pumping or lifting by a bucket. In this particular construction stage, obviously the steel joist is not benefiting from the welded studs. So the first load case is that we need to check the joist for the non-composite loading, that being the wet weight of the concrete and any construction workers that are standing on the floor surface. So one of the loads that we ask of the engineer record is their required construction loading during the actual construction of the floor. So the joist manufacturer will check this particular construction case. And like I said, this is a temporary condition. Once the concrete hardens, why then you're at a more of a service load case. The Nucor and SGI have completed a number of UL fire tests. This is just a picture of some photos I took at a UL fire test. And you can see here in the lower bottom portion of the slide, the actual joists are loaded with jacks. The joists are loaded to full design load, at which point then UL fires up their furnace chamber below. This is a photo I took looking into the fire chamber through one of the ports, and it's really like looking into hell as far as the heat that is generated. And of course, UL has a standard time temperature ASTM curve that the chamber exposes to the joist. In this particular situation, the joists were protected with spray-applied fireproofing. So that is one common way of extending the fire protection for a steel joist. The actual application of the fireproofing, I've seen it done in several different manners. It's typically done by spraying, obviously, the fireproofing onto the individual members of the joist, particularly for deeper joists. For shallower joists, I've seen where the fireproofer will unroll a roll of fabric scrim onto the side of the joist, attach that. That will tend to reduce some of the overspray, but that's typically only done for joists that are medium depth or shallower. So the actual application of the fireproofing goes quite well. There are special nozzles that can be obtained for directing the actual spray application of the fireproofing onto the individual joist members. As far as the actual UL ratings, the SJI Composite Joist catalog has tables within it which lists spray-applied fire ratings. And this particular table here that I'm sharing with you lists 1 through 3 hour fire ratings. And you can see this particular table here is for a 2-hour rating. And so you can, there are a variety of different UL numbers that the engineer architect can specify. Also, the other thing, of course, is there's minimum thicknesses of concrete and either lightweight or normal weight. Some actual ratings list both. So this is an easy way, if you need a particular rating, these tables are available and you can reference these UL design numbers. There are also tables available for membrane protected composite steel joists. And so this table here shows 1, 1.5, 2, and 3 hour ratings. And you can see here there are actually exposed grid, which is like a ceiling tile type of application. And then also there are listed gypsum board applications. So with that information, you can reference particular UL design numbers. The International Building Code, like I mentioned, in 2015 has a section on 2207 on steel joists. So in general, the design, manufacture, and use of composite steel joists shall be in accordance with the SJI CJ-Series. These are some responsibilities listed here for the registered design professional. Shall indicate steel joists and joist girder designations, the joist and joist girder design loads, the layout of the joist, end supports for the joist, if there's any anchorage for the bridging design, and if there's any uplift loading on the particular joists themselves. Construction documents shall also indicate if you've got any kind of special loads, if you've got concentrated loads, non-uniform loads, end moments, or any kind of special connection forces applied. That is information that needs to be provided to the SJI joist manufacturer. Generally, as far as composite steel joists, typically those are parallel chords, members. As Sam mentioned, we can design for special Varandale openings. So if you've got requirements for those, Ideally, some sketches showing the location of where those Varandale openings are located would be very beneficial. If you've got any kind of extended ends for the joist, if you have any type of special live or total load deflection criteria, that needs to be specified. It's very common, for example, at the edge of a building, where if you've got windows, I've seen where, say, there would be a deflection limit of no more than, say, a ½ inch to make sure that the window installation is easily accommodated. And of course, the actual design for the composite slab is the engineer's records responsibility as far as the actual selection of the steel deck profile and gauge, slab thickness. If you've got any additional reinforcing that you'd like to put in that slab, along with the specifying of the concrete compressive strength and concrete unit weight. As far as the joist manufacturer will design the CJ-Series joist per the SGI specification. The joist manufacturer will determine an optimal shear stud diameter and quantity of shear studs. The actual joist manufacturer will provide design calculations for the composite joist along with a cover letter from the joist manufacturer's registered design engineering professional. The joist manufacturer will provide steel joist placing plans that will show the location of the joist, if there's any special end connections for the joist, it will show the location of the bridging and any type of bridging connections. I get many times questions from engineers asking what is a good application of where I should use CJ-Series joists. And this slide is really kind of a summary of helps to answer that question. If you've got joists, I would encourage you for CJ-Series joists to place them at 8 to 12 foot on center. I see a lot of jobs where the CJ are placed, say, 10 foot on center. I would discourage you to place CJ-Series joists 4 foot on center, and because it's too close, it's too light of loads. So many engineers, I guess how I would look at this, I would look at this as CJ being a replacement for a wide flange beam. Engineers typically are not going to place a wide flange beam 4 foot on center. They're going to place a wide flange beam 6, 8, 10 foot on center. So you need to think of the CJ as really a replacement for a composite wide flange beam. If you space out the joist farther on center, say 10 foot, you're going to have fewer joists to erect, which is going to be very beneficial when it comes to reducing crane erection times. You're going to have fewer joists to fireproof. You're going to have larger joist top chords, which, as Sam mentioned, to get, say, 220 studs per hour, you need some fairly decent sized top chords. So it's going to make the installation of the studs a lot quicker and easier. You're going to end up with larger chord sizes as far as thickness, and also if you actually space the joists out, you're going to get a more optimal utilization of the joist and the composite steel deck at the wider joist spacing. The SGI CJ-Series catalog has a design parameter checklist, and this is just a list of typical input values that the SGI manufacturer is going to need to design the composite joist. So this is just a copy of that checklist. Of course, we obviously need to know the depth of the steel joist. We need to know the span for the joist. If we need to look at the distance to the adjacent joist to the left and to the right. And if you've got an edge distance, say for a spandrel, one of these distances is going to be the distance to the edge of the slab. Type of floor deck. Typically what I see are 1-inch, 2-inch, and 3-inch composite decks, the same as what you would see with a wide flange beam, depth of the floor deck, slab thickness above the deck, concrete unit weight, and finally concrete compressive strength. With typical concrete compressive strengths, I see 3, 3.5, and 4 KSI are all very common. As far as the actual loads that are on a composite joist, of course, item 1 is essentially the non-composite construction dead loads, which are made up of the concrete, the joist and bridging, the steel deck, which we total up, and finally the construction loads during concrete placement. So, okay, then we have composite dead loads. We've got partitions, mechanical, electrical, fireproofing. Those are added up for the composite dead load. Composite live loads, we tabulate those. Then, of course, what we do, we apply load factors, typically a 1.2 factor on the dead loads and a 1.6 factor on live loads. The actual, we talked about cambering and deflection, so this is a point where you can call out the preferred amount of camber. Like I say, typically what I see is people select this option 1A, where you're cambering for the full non-composite dead loads of the slab, the joist, and the steel deck. So, and then if you've got any type of special live load deflection limits for whatever reason on the slab, you can call those out. Okay, what I'm going to do, I'm just going to quickly go through an example, typical floor design for a composite steel joist. And in this particular case, we're looking at a 30 by 50 bay, and we've got the engineers selected a 10-foot joist spacing, and we're looking at a 2-inch deck, 18 gauge, normal weight concrete, concrete compressive strength of 4 KSI, and we have a total slab above the deck of 3.5 inches. We're going to camber, in this case, for 100% of the non-composite dead load, a percentage, 50% of the composite dead load and 20% of the composite live load. Maximum live load deflection of L over 360. We're going to, in this particular instance, we're going to look at a 30-inch depth for the 50-foot span. We're going to have, I mentioned the 10-foot spacing to the joist left and right. From that, we can then tabulate our loads, non-composite construction live load. The engineers called out 25 pounds per square foot, which is quite common. We can tabulate these. We come up with a total factored composite load of 2,296 PLF. So the SGI actually has tables within the standard SGI specifications. You can catalog. So what you can do is we're going to come in at the 50-foot span. We picked a 30-foot depth. We had 2,296 PLF, which puts us over onto the second page of the load table. So the 2296 is between 2,200 and 2,400. We come down at in our 50-foot span. We see some information. The weight of the composite joist, 38 PLF. The W360, which is the live load, which results in a L over 360, is 1376 PLF. This joist would have 54 3/4-inch diameter studs. Effective moment of inertia is 4,000, and it would have 2 rows of horizontal bridging. There's also a second set of tables where you can actually obtain additional information about the actual bridging for the composite joist. So we can look at that table, our 50-foot span, 30-inch depth. We come across to our 2,296, and we'll jump up to 2,400 PLF because that's conservative. And you can see in this table, it gives you the bracing force in the bridging is 1,100 pounds. It even provides you the size of the horizontal bridging material, 1 3/4 by 0.170, and the non-composite moment of inertia for the joist of 1520. Another table that's available in the SGI composite catalog is, obviously we talked about running ducts. This is just a simple table. Given the depth of the composite joist, it gives you an approximate size for round, square, or rectangular ducts. As Sam mentioned, a lot of the engineers now utilize BIM, and so the SGI manufacturer can provide BIM models for the composite joist, which is very helpful as far as coordination of the HVAC through the open panels of the composite joist. Sam talked a little bit about the load designation. So in this particular case, we've picked a 30-inch CJ 2296, 1168, 444, and that particular joist has top chords 3x3 by 313, nice wide chords for welding of the studs, bottom chord angles of 4x4 by 3/8, weighs 38 pounds a lineal foot, 3/4 inch diameter studs, which is the most common diameter stud you're going to see on composite joists. And we've got 54 of these, which is essentially a stud every foot. Just kind of rule of thumb, that's typically you're going to be somewhere near a shear stud every foot of the joist. Is quite common. As far as I just looked at comparing the weight of that particular design, which was our 30 CJ 2296, with several other alternatives, as we had determined that joist weighed 38 PLF. If we looked at, say, a 21 by 55 beam on 10 foot, and we were needing to run the HVAC below, that is going to be heavier. It's 55 pounds versus 38 PLF. If we looked at a non-composite joist with the same depth and load, we would end up at 58 PLF, which is considerably heavier than the 38 PLF. And if we were to look, say, at a non-composite beam, which people typically would not use, but if you had a 21, you would have to go to, say, a W21 by 93 or W30 by 90, which is much, much heavier. So composite joists on these longer spans will almost always come out with much lower weights and lower cost. Another question that I receive many times is, what's the vibrational characteristics of composite joists, CJ series? There's some very good information that the SGI has a Technical Digest 5 on vibration. The AISC has a Steel Design Guide 11, which covers the vibration of steel joists. The SGI recommends the use of Dr. Murray's Floor Vibe 3.0. It's a software that you can obtain, shown the website here. It easily does the calculations for a composite steel joist vibrational check. This is just a picture I took a number of years ago. I was with Dr. Murray measuring a vibration on a floor. And actually, just a week ago, I was on another floor with Dr. Murray. So Dr. Murray is still actively involved with vibration and is a leading expert in the U.S. when it comes to floor vibration. So, one question that I get many times is, how does the vibrational characteristics of a composite joist compare to a non-composite joist? And the answer to that is they're identical, in that even with a non-composite joist, the assumption is that the joist is composite. So the actual effective moment of inertia show this is it's actually from Design Guide 11. There's actually a reduction in the moment of inertia due to the compression in the web effects of the actual web members themselves. So there's a standard way for coming up with the effective moment of inertia of a composite joist. This is just a screenshot from Floor Vibe 3.0. Shows some of the input parameters. You can put in the slab thickness, the loads. Actually, there's a special screen in FloorVide for composite joists where you can actually put in the depth, and these loads on this screen here are service loads, not factored loads, so that's a key point to note. And you can then calculate it, and in this particular case, the ACE of P over G was 0.446, which is less than the 0.5% of G suggested for walking criteria. So this floor met the suggested vibration criteria. The SGI has a free downloadable tool. Go to the SGI website. You can download this as an Excel spreadsheet. This is an easy way for estimating the weight and size of composite steel joists. It's in our SGI's floor bay analysis tool. You enter the depth of the joist. It will then you can enter in actually unit costs for construction materials. It actually checks the joist and the steel deck, and you can then actually run comparisons of you can save your designs, change the parameters, and compare. In this particular instance, we compared two different joist designs. So it's an easy way to optimize and determine what is the most efficient composite joist depth and spacing, etc. As far as utilization, there are thousands and thousands of floors have been constructed with composite steel joists. Kohl's department stores has over 1,100 mezzanines in their stores which have composite steel joists. These mezzanines are typically near the front of the store. They've got shallow composite joists, and the thing that really drove them, they had required headroom of like 8'6" on these mezzanines, and so what they wanted to do is the composite joist allowed them to reduce the overall outside wall height for the entire building. So if you can reduce the wall height by say 6 inches or 12 inches on a 200,000 square foot building, it's a significant savings. So they have essentially standardized all their mezzanines using SGI's composite joist. This is a store actually out in Arvada, Denver, that had composite steel joist in the actual floor of the store, 200,000 square foot store, and they were expansive soils at this particular site. They augered down to bedrock, put in pier type footings. That was much cheaper than excavating out and bringing in compacted fill. They used joist girders between the concrete piers, composite steel joists. You can see here the top chords of these joists were left unpainted. Menards has utilized composite joists in a number of their stores. This is some pictures I took in their Minneapolis store a couple of years ago. Used them in their second story of their floor. It spans at 20 to 40 feet, joist at 5 foot on center. Live loads of 200 pounds per square foot. So you can see there's some heavy loads. You can see here all the the types of construction materials that they'd have stacked on the floors. It worked awesome for them. You can use composite steel joists for really long spans. This is a 117-foot span in Kansas City. The owner insisted that there be no disruption to their computer facility on this ground level. So the engineer augered actual footings down, placed concrete in for the footings, erected the steel outside of the existing operational computer center, and erected the 117-foot composite steel joist. I visited this floor, and the floor was really felt good from a vibrational point of view. There's some things about really long spans. Particularly with bridging, it's beneficial if you, at the edge of the building, you do not use X, but use horizontal bridging. course, we mentioned Sam shared the flush frame. This is a very common type of in connection. There's been over 20 buildings constructed in Boston in the last 7 or 8 years by McNamara Sylvia. Pretty much all their composite joist buildings utilize this flush frame. It works really, really slick. It allows the girders to be composite. They can drop in the joist easily with a crane and bolt them up. It's very, very quick, very efficient, clean system. And as Sam shared with you, of course, pretty much all these projects have barrendales at the center of them. Just to give you an idea, this is a 17-story structure, 30-inch deep, 45 to 59-foot spans, joist 10 foot on center, and so spray applied fireproofing. So this is very, very classical. Like I say, there's over 20 buildings, high-rise buildings that are in Boston right now. As far as the good reference for composite joist information, back in 2002, I authored actually an AISC engineering journal on composite steel joists that summarizes a lot of Nucor's composite steel joist research. So I would encourage you to take a look at that. It shows you a lot of the background as far as the actual research behind that Sam mentioned. So in summary, composite steel joists provide a very efficient and economical floor system. You can see that the floor-to-floor heights can be reduced while utilizing composite steel joists because we can run the mechanical systems through the open web of the steel joist, through the actual webs or through special designed barrendales. With composite joists, you're able to span very long distances, up to 120 feet if you need be, which gives the building owners love that because it gives them more flexibility as far as layout of floor plans. There's no columns impeding someone's view on the outside. Also, with composite construction, you're going to see significant reductions in the weight of the structural framing because you're now locking the concrete to the steel joist, which results in significant savings for the building owner. As far as actual references, I would encourage you to go to the SGI website, and you can download the SGI second edition standard specifications and tables. There's also, I mentioned the SGI floor bay tool that is available on the SGI website. This is a free tool. It's a very easy way to come up with preliminary estimates as far as actual weight and costs for CJ series. So